Alrighty. Hello. How's everyone doing? How are you doing? I hope you're doing alright. In this little video, we're going to go over problem 2.3 of Griffiths E&M. So this problem here, where you're given some kind of charged kind of rod with some length L, and you want to see what's the electric field here at the point perpendicular to sort of the edge of this rod. Okay. Okay. So then I do work these problems out before these videos just to, okay, here we go. So we're given some kind of rod. Let me kind of draw it here. Something like this. It's not perfect, but it should get the point across. And we're evaluating this point P here. The rod is kind of implied that it's fixed. It doesn't move. I'm going to say that point P is positive. Okay. Again, even though there isn't a charge there, we assign it to be positive so we can evaluate where might the electric field go, provided there was a positive charge there. So uniform line charge lambda. What lambda means is specifically charge over length. Okay. It's also referred to as linear charge density. So how many charges are there per unit length on this kind of rod? Say this is relatively speaking dense, kind of dense, when compared to something like this, where the charge density is less dense on this rod. Okay. But at this point, we have the rod is big enough to where we can't really individually see the individual charges because they're small. And so in this kind of limit, we can refer to as the individual charges as infinitesimally small. Length L. So what's going to happen? What's going to happen is that we're going to have to analyze each segment in this rod essentially and see, if this rod is positively charged, and see how will the electric field respond. Okay. We're going to evaluate it for the entire thing so we can get the net electric field all throughout. I think this is a good way to show off a little bit of calculus, because we can do this forever, right? How many times do we have to do this to really get the full rod? Well, we do it an infinite amount of times. So we can employ some calculus to figure out the sum of all those electric fields. For now, I'm just going to choose one arbitrary point, one arbitrary charge element, dq. Supposing this entire thing is charged, this little element here will be an element of charge. And it's some distance r from the point. There's a little bit of symmetry here, or a little bit of kind of geometry here that we can exploit. The fact that point P is perpendicular to the axes of the rod is just at the edge. And here's one thing. You can choose sort of your angle of analysis here, which, you know, as you kind of move on and you scan the entire rod, this angle will be changing. But I don't really want to do it like that. I'd prefer here, this angle. And the reason is because, I mean, if you remember something about the unit circle, according to trigonometry, once you can either go around to get that 360, or, you know, suppose this is like, I don't know, 30 degrees. I could go this way, end up over here at negative 30 degrees. And so if I had a longer rod, I'm going to leave that for you to figure out. But essentially what happens is that once you, and there's a longer rod problem, once you scan through this entire thing, some of the electric fields are going to cancel out with each other, and it's encoded in the math. Because if you set this to be 0, once this angle becomes 0 here, once your R is perpendicular like this, and you start scanning this way, you're going to get negative angles. So you're going to get a canceling effect encoded in the mathematics. But you know, I guess I'm going off on a tangent. But yeah, let's go back over here. Now, again, if there was a particle here, because I'm assuming this to be positive, just for simplicity's sake, the problem doesn't really tell you, but you know, this problem is more so like you get to choose some things. You can make it negative, see what happens. I'm going to say that this charge is mostly, this rod is mostly positive, and so the particle would go that way, and so the electric field must also go in that same direction. Now let me move this point P somewhere over here. Alright, so now we have to kind of draw the components of this vector. Okay, we extend the y-axis and we extend the x-axis. I'm going to say that y will be red. Put this somewhere over here. Say this is EY. That this here is going to be EX. Okay? And check this out. These lines are kind of bisecting each other. Is that what they're crossing each other? And so this angle here, just through geometry, is going to be exactly the same as this guy. And this vector here, we could also say that it exists over here as well. Okay. And we have a little 90 right there, so both of the EY and the EX components are perpendicular to each other, orthogonal to each other. Now, yeah, so it seems in this problem there isn't really any cancellations of components. They're going to add up to certain numbers, certain equations, and so we have to solve for both of them. In the previous problem, you had some cancellations happen and you could just focus on one component, but in this case, both of them, they don't really cancel each other out. There's not really any cancellation happening. So now we kind of have to formulate the field itself as a vector with a y component and an x component. So, right? I pull out the vector notation. Okay. Ex, Ey. And we have to figure out what these are. Okay. Now, so now we're going to go a little further. Now we have to define these EXs and these EYs. We went to the problem, we figured out that we have to figure out these guys. Now we have to figure out what these guys actually are. So in our case, if I take this triangle and I flip it, okay, I'm going to get something kind of like this. Now, according to trigonometry, we can define so let me go ahead and bring this down to somewhere that's a bit clear, like over here. We can define EX as let's be a bit cautious here. So yeah. All right, let me be a bit more organized with the notes. So let's evaluate the cosine theta of this triangle here. Cosine theta is going to be equal to EY to the magnitude of this vector here. Then sine theta of this triangle here is going to be equal to x over the magnitude of this triangle. Now, recall we're using here a a point charge, so to speak. It's an infinitesimally small length of this kind of rod here. But the magnitude itself, we can relate it to the electric field of a point charge. And so this E here, we say, all right, 1 over 4 pi Q over R squared. Okay. Yep. So that goes there for both of them. So in our case, so we've kind of defined this a little bit here. We can say now EY is equal to 1 over 4 pi epsilon naught Q over R squared, right? We just do a little algebra and move that over there. Times cosine theta. And we do the same for this component. So EX is equal to, okay, 1 over 4 pi epsilon naught Q R squared sine theta. Okay? Let me go ahead and move this over here just for symmetry's sake. Move this somewhere towards the middle like this. Yeah, I think that looks nice. Okay, so again, we can express here, so X, okay, we can express these cosine thetas, these sine thetas, as geometric ratios, because again, this is a Pythagorean triangle. So let's do that. So in the case of our triangle here, so again, the length X, R, Z, right? We're just copying that triangle down. Okay. The angle is up here, notice. So that means that our cosine side is sort of adjacent to the angle over hypotenuse. Cosine theta is equal to C over R. And that leaves sine theta equal to opposite over hypotenuse X over R. Well, hopefully I didn't make too much sound on the mic. And again, we're dealing with Pythagorean triangle here, so the hypotenuse is defined as, can be defined as its components. Meaning that R squared is equal to X squared plus C squared. Pythagorean theorem, the one we know and we all love, okay? Meaning that R, take the square root of both sides, plus minus, actually, yeah, what we choose here is actually very important. So we can't just arbitrarily choose this to be positive, not now at least. We determine that in the end, because again, that's going to determine the directions of the components. And we want to make sure that we choose the right sign so as to make the answers be correct with kind of what we know the system's going to behave like due to this kind of vector analysis here. Okay. So we're going to keep this undetermined for now. It's either positive or negative. Okay, so now we substitute that r squared in these equations, okay? And then again, we substitute these r's here for these guys, okay? So let's do that. So now EY is going to be 1 over 4 pi epsilon naught Q x squared plus c squared cosine, which is c over plus or minus the square root of x2 plus c squared. And then EX, yeah, 1 over 4 pi epsilon naught Q, same kind of ordeal. And then it's going to be x over positive negative square root of x2 plus z squared. Okay. Now, so you see, these problems, yeah. Unfortunately, this one, I might not be able to make it under 30 minutes without explaining the things as thoroughly as I can. But, if you see that this video is going to be however long it is, don't get too scared. I'm just kind of over-explaining these things. Theoretically speaking, these problems don't take as long once you know what you're doing. Okay? Like, if you're in a position where you don't have to explain anything, you might be able to get one of these problems done in 10 to 15 minutes. Okay? But in my case, okay. All right, so let's continue. Now, Yep. Okay, so now we have to think about the differential element, because we formulated these equations for Q, but in reality, we are dealing with a dq, a differential element, an infinitely small element of the rod, which, if we think about, anyone that might be doing more advanced physics, right, like quantum mechanics or something like this, where the idea of a charge can't be continuously like super infinitely small. There is a limit to how small a charge can be as the charge of an electron so far. But in our case, we're dealing, we kind of think about, okay, this might be a macroscopic object. This might be a big rod, something I can hold. And at that point, the amount of electrons in your macroscopic object are like literally millions and billions. Like you're gonna have like Avogadro's number, which is a really big number in like a really small part of your rod. Now you have a big one that, okay, so you can, at that perspective, where things are just so small, then you can refer to a charge like this as infinitely small, and the approximation is going to be fairly good. Okay. But okay, so dq, we have to sort of look at this equation a bit further. Okay, so we take a little pause here. Pause, okay, from these equations and so forth. So lambda is equal to Q over L. So we do a little bit of algebra and we can say something like this. We can say that lambda is equal to the linear charge density times the length. That evens out the units and you end up getting charge back, so to speak. The unit charge, I guess. You could say, now suppose we take a differential element of this charge, and now you take a derivative with respect to L, or maybe I should more explicitly say, like, okay, dq dl, when you take a derivative and there's an L, the L goes away. Okay. You know, is it right for me to assume that if you're looking at this, you know calculus? I don't know. I don't know. But in the case you don't know what derivative is, the derivative is, or now you're looking at these infinitely small objects, and so the operation goes as, you know, if you have some kind of, I don't know, like 2 right here, you bring the 2 down, and now it becomes L1, 2, but, you know, in our case, there's a 1 here, so you bring the 1 down, and now you have 1L, which is just L. But, you know, 1L0 and L0 is just 1. So basically, you end up with the L fizzling away. Did you guys hear that cat? There's like cats outside. They be, I don't know what they be doing. But yeah, and then that's your, you taking a differential. Now with a little bit of algebra, we can move this to the side right here. And boom. Now we have our differential charge defined in terms of a differential length. Okay, so now, I mean, if we think about it, yeah, I mean, that makes sense. Differential charge is equal to the linear charge density times a differential element of this rod. I mean, that's fairly interesting. And now, since we're dealing with the x-axis here, okay, this rod is in the x-axis, we can say lambda dx, because it's kind of implied like we're gonna sum over this entire rod, and we're gonna do that with the x parameter, because x is in some sense like a variable thing. It grows. L is kind of this determined, so we're gonna do the sum. So we're gonna do this all throughout, all until we get to L, the length of the rod. And we're gonna do that with x. Now, with that being said, now we can go back to these equations and take a differential of these equations. So now, dE y, kind of go like this a little bit. So 1 over 4 pi, I mean, you write this 1 over 4 pi epsilon not so much that you just remember it. dq over x squared plus c squared z plus minus x squared plus c squared. And now we know the definition of this. And we want to choose the one with the differential element x because we are going to integrate with respect to these x values here. Okay. Now, dy 1 over 4 pi epsilon naught lambda dx over x squared plus c squared c plus minus x squared plus c squared. Okay. Put a little star right here. Now we're going to do dex 1 over 4 pi epsilon naught lambda dx x squared plus z squared. And the only thing that changes in the ex component is this argument here, which you still have this kind of x plus or minus x squared plus c squared. Put a little star over here. Okay. Now, so yeah, we were forming these equations. So these are not really not for full rod. Okay. It just helps us to get there. Okay. And now this is more adequate descriptions. So now this is for differential. So actually, let me kind of here we go. Okay. These equations now really represent what we're trying to do, which is for this kind of differential element of this rod. And now, this is where the magic happens. We're looking at an infinitely small portion of this rod, and now we're going to sum infinitely amount of times. I mean, infinitely, like, I'm doing like something finite. Imagine this being completely smooth an infinite amount of times, all the way till we get to L. And this is how this looks. So now, what we do is we have, let's do this. Boom. We add that little symbol there, and this is your integral symbol. Boom. Boom. Add it on both sides. Now, this argument here becomes just EY. So now this is a true EY component, the one that's summed over the entire rod. Okay. And you know what? We're going to bring out some of the constants. We're just going to leave inside that integral things that aren't constant, like this x, or anything that depends on x. Okay. 1 over 4 pi epsilon naught. This lambda must come out. The z must come out, because that's constant. Integral from 0 to L. This is what I was, saying, like from 0, because we're going to define this end of the rod here, this end as being the 0 point, and this other end as being just L, okay? So that's our bounds. Now, for simplicity's sake, because these are multiplications all throughout, I can move this sign wherever I want, just to make it more convenient. So I'm going to move it over here, plus or minus. We'll determine this kind of in the end. And now we're going to have that then we're going to move this guy all the way over here. C comes out, lambda comes out. Now we have dx. And now we have x squared plus z squared times the square root of x squared plus z squared. And this here can be defined as like this. So we can put a 1 here, and that makes this argument exponentiated to 1 will still be the same thing. And then 1 plus the 1/2 from here, okay, because this here turns out to be 1/2. It's 3/2. And now we can have ey over here as plus minus lambda z over 4 pi epsilon naught, integral from 0 to L dx over x squared plus z squared 3/2. Okay. Alrighty, so now what? So now, I mean, this, you remember this equation here? There's the EX component. Let me just make sure here. EX, EY. Yep. Yeah. Okay. We have our EX. Now we have the EY component here, so we can, boom, place it in this little placeholder area. Through 2. And now we have to figure out this EX here. Where EX is, again, we bring out sort of the constants out. In this case, we get something like this. Lambda 4 pi epsilon naught from 0 to L plus or minus dx over x dx over x squared plus z squared 3/2, because we have this same kind of situation here. We have both of these, the exponents of both are essentially adding up. There we go. So now our electric field equation looks something like this. Plus or minus lambda 4 pi epsilon naught 0 to L x dx x squared plus z squared 3/2. Now you put a little parentheses, and then you put this other equation in there. Kind of go over here, lambda z plus or minus 4 pi epsilon naught 0 to L dx x squared plus z squared 3 over 2, and we close it. And this is our vector. This is our vector equation, still in like this integral form. We can solve these guys analytically. We can, and you know what? We should do that. But I think most of the physics kind of ended, so to speak. It's not until we actually solve the entire thing, you know, we have to now go through math to solve these guys. But the physics, like setting it up, I'd say we got there. So we do math, and the last physics is after the math, where we have to figure out, okay, what would be the appropriate signs to choose so that the vectors, the components, work out in the way we set them to be through just this kind of basic components physics, component analysis. Okay. But all right, so one of these integrals is easier to solve than the other. Let's start with the easy integral. Okay, so now it's going to go from physics, now we're going to go to calculus 2 level, so to speak. Because now we're going to solve these integrals. So all right, let's go ahead and have this EX here. Epsilon naught 0 L x dx x squared plus z squared 3 over 2. Oh yeah. You know, so we're going to be doing math, but at the end, the physics that's for the end, when we figure out these analytic expressions that these solutions are going to yield, is not only figure out what are these plus or minuses, which one's plus or which minus or something like this. It's also figuring out if the equation is right. Right? Because I mean, I know this is right. I worked it out, but you know, how do you know they're right? We need the analytic expressions to, you know, to kind of determine that, so to speak. But yeah, anyways, calculus. Okay, so here we can do a u substitution. U x squared plus z squared. Okay. And now this is a constant. This is a variable. The differential of this will be 2x. And because it is constant, it just becomes 0. Then dx, because we took a derivative. And now we want to move this 2 to the bottom, a little bit of algebra. And now you see we have these dx's terms here, so we can substitute this in there for those dx's, for those x dx's. Okay, the 1/2, we have to remember this. dx's, okay, so now that's du. U, okay. And 3 over 2. Now you have this, you can, when it's in the bottom, it's 3 over 2, the exponent. But to make the calculus a little bit easier, we can do, you know, it's equivalent to say u negative to the power of negative 3 over 2 du, and then the bounds become this function of u, you know, because the bounds do change relative to how you took the substitution here. But I'm not going to compute them out. I'm going to wait till the end, and I'm going to back substitute to the original bounds when I, you'll see. So now we take an integral. The calculus with derivatives, you know, you have 3 over 2, you put this down here, so negative 3 over 2, and then you go down. So negative 3 over 2 minus 1 would be negative 5 over 2, and that's your derivative, so to speak. When we're taking an integral, you have to go up. You have like 3 over 2, now you have to be like, okay, we're going to go up plus 1, and that's going to be negative 1 over 2, and then this here, you have to put it at the bottom like this. Yep. So yeah, so you end up getting this. So EX plus and minus lambda 4 pi epsilon naught let me just make sure everything's good. Yeah, the z's over here. Okay. 1 over 2. And now you have 1 over 2 negative u to the power negative 1 over 2. Then you're like, okay, let me put the bounds, u0, fundamental theorem of calculus. These two are going to cancel. So now your EX becomes plus minus lambda 4 pi epsilon naught. And yeah, I mean, there is a negative here. So let me put here times negative 1. Just hold it there for now. And now u, we back sub u back in here. Now we end up with x squared plus z squared to the power of negative 1 over 2. And now we can get rid of these kind of u functions, 0, the function of u, and function of u with L. We can get rid of that. Now we can go back to the original sort of bounds here. Negative 1. And now we can do like, okay, so we plug in L squared plus z squared to the power of 1/2 minus, oh yeah, this is the fundamental theorem of calculus. Yeah, minus 0 squared plus z squared. So you just copy the same sort of form, minus it. There you go, there you have it. So, and now I'm going to distribute this negative in there, just so that it's not like awkward. Now we're going to have 1 over the square root of c squared. Okay, and this is a negative, so you bring it down and you're like, okay, 1 over c squared 1 over 2, but we know that to power 1 over 2 is the square root, and negative, and that becomes negative times a negative becomes a positive, so that's why it's a positive here. Negative times a positive, now it becomes a negative. 1 over square root L squared plus z squared. And now when you have some number to the power of 2 inside of a square root, this cancels out, meaning that EX plus or minus lambda 4 pi epsilon naught 1 over c minus or square root of L squared plus Z squared. And here we go. All right, so that's our expression for this kind of EX term. Now we have to do some limit analysis on it, just to make sure it's like correct, I guess you could say. So, okay, what happened here? Okay, so, you know, so again, we sort of draw our little setup here, L, Z. So now we want to suppose, okay, so as L goes to 0, what happens? Meaning that not L equals 0 as it goes to 0. Meaning that L is infinitely small. Meaning that L is like something like this. Okay, it's not 0, it's just like really, really small. Okay. I don't know about you, but I mean, that kind of looks like a point charge. Let's see what we get. So, okay, so EX plus minus lambda 4 pi epsilon naught 1 over Z minus 1 over square root 0 squared Z squared. And again, you get this type of situation here, where the square root is going to cancel the square on the Z. You're going to get 1 over Z minus 1 over Z. That's just 0. This whole thing is just 0. Does that make sense? Well, think about it. If you have a point charge here, both of these are positive. You're going to have an electric field that way. There's not going to be any EX component nigh. Therefore, we got a good equation. It kind of models what we expect, which is there's going to be no component in the X direction. Now, what about as L goes infinity? What will that produce? As L goes infinity, okay, meaning that now L is just an infinitely long rod. What will we get? I guess that's going to be fairly interesting. Now, EX plus or minus lambda 4 pi epsilon naught 1 over Z minus 1 over square root infinity squared plus Z squared. So now Z is going to be tiny in comparison to this number. So we can just say like EX plus minus lambda 4 pi epsilon naught 1 over Z minus square root infinity. This is still infinity, it's a really big number, meaning that this goes to 0. If you have infinity over 1 over infinity, that means you're dividing an infinite amount of times. The little divisible, if you have a length, you have a rod, you're dividing it into many, many, many parts. Infinitely many parts. That means that the little shaving is going to be infinitely small. 0. This term goes out, and then you have this very interesting very, very interesting. If your rod is infinitely long, you'll get something like this. Which means that the electric field can only get so big. Yeah, because you have your linear charge density here, and that's given, and then Z is going to be constant, so there's going to be a point where the electric field in the X direction is going to stop growing. So that's more like a physics thing, like, you know, is that correct? We don't know. I mean, it's predicting something. This is what you get out of physics, right? These equations is predicting something. Now, you'd have to validate this with some kind of experiment, maybe. But okay, so yeah. So originally, Griffiths was asking, okay, do the limit analysis on Z. What happens as Z goes to infinity? What happens to Z is Z goes to infinity. Let's see. So as Z goes to infinity, this EX is going to be 0. Because again, I mean, you know, if you look at this, right? Z is infinity, that goes 0. Z is infinity, that goes 0. The whole thing becomes 0. And you get this kind of situation where you're just so far away from the rod that it itself looks like a point charge. And so, you know, when you have 2 point charges, the electric field is going to be in the direction of the connecting line. Okay? Not really in the perpendicular direction. So I'd say that, you know, sounds like a good model. Okay, so I'm going to say that EX checks. And now we choose whether it's positive or negative. Okay, so yeah, so yeah, so let's kind of think about it. So if L, yeah, so this number here, fundamentally, I believe this number is going to be that 1 over Z, you have L, if L is greater than Z, and that means that, yeah, I suspect that this number is going to be big, relatively speaking. Let's kind of do a little test. Let's do a little numerical test. Okay, so let me carry this equation down. Copy. Paste. Okay, here we go. Suppose that LZ is equal to, I don't know, 2 meters. No. 0.5 meters. How about that? And suppose that L is equal to 1 meter. Okay? So EX is then going to be lambda 4 pi epsilon naught 1 over 0.5 minus 1 over square root of 1 squared plus 0.5 squared. What will this number yield? All right, use a little calculator here. So say lambda is, you know what? I don't care about lambda. It's some number. What we care about is whether this here is going to be positive or negative. So here we go, 4 pi epsilon naught. So 1 over 0.5 minus 1 over the square root of 1 squared plus 0.5 squared. Something like this. Yeah, this number is going to be positive. What if this is, I don't know, what if this is like 2? This is 4 squared, 2 squared. Here we go. Over 2 minus 1 over square root of 4 squared plus 2 squared. Yep, still going to be positive. So if you have the relation where the rod is bigger than the length of how far the point is from the rod, you're going to get a positive number. And EX from the physics here, way back over here, it has to be in this negative direction. So we're going to choose this initial, point here to be negative. So, if L is greater than Z, then we have to choose EX to be negative lambda of 4 pi epsilon naught 1 over Z minus 1 over square root of L squared plus Z squared. And that'll give us a negative EX vector component. Yeah, so that's an hour. That's yeah, we've been here for an hour. So you know what? I'm going to do that other one. I'm going to do it. By this point, most of the physics and stuff has been talked. Now we're just going to do the other EY component, which is going to be a harder one. And if you need some review on trigonometric substitution or something like this, I suggest you stay, because for that specific component, we have to use trigonometric substitution to actually solve the integral. Or you can look it up in a table. But I like trigonometric substitution. Okay, here we go. So EY is going to be equal to here. This little fella right here. Copy. Okay. Paste. Alrighty. So now, this is interesting because now we have this form. We can't do a U substitution. So you take the derivative, you get 2x, and there's no x up here. And then the bottom, there's square root and all this type of stuff. Trigonometric substitution. That's what we have to do here to work this integral out. So okay, let's go ahead and, so IY, let's call it IY, 0L dx over, I want to say the square root x2 z squared or to the power 3. And this is the same thing. Remember, the square root, the argument over the power 1/2 is the square root. And the 1/2 here, 1/2 times 3 is equal to 3/2. So the square root is kind of hidden in there a little bit. And now here. The trigonometric substitution goes like this. It goes like this. It goes like a squared plus b squared x squared. I think it's something like this, square root. And that's going to go into x being a over b tangent theta. Yes. I think I remember correctly. Okay, so in our case, we have square root x. Let's kind of reorganize it a little bit. Z squared plus x squared. And notice the b, there's no b here. There's no b term. Yeah, this is 1. We can say 1 squared. So x is going to be z, just z. See, because here you have a squared, you only carry the a. Z over 1 tangent theta. Then x equals z tangent theta, because the bottom is just 1. Z tangent theta. The derivative tangent, this is a constant, secant squared theta d theta. Okay. Now, so that's kind of your, how you do your trigonometric substitution. Of course you want to say tangent is equal to arctangent, or I'm going to write it like this, inverse tangent x over z. Now let me go here, let me write it, trigonometric substitution. This is the calculus 2 method we're employing to actually solve this integral. And okay, so now we have to actually do the substitutions. So now Ix, what is this? No, Iy, because we're just looking at the integral. We're kind of just leaving these constants to the side because we'll put them, we'll snip it back together later. This is sort of the area of importance here. And the bounds are going to change. The bounds are going to be, because now, you know, the function is going to go from like a function of x to a function of theta. It's going to be theta 0, theta L. Okay? Which theta L is, so it's this function here, but instead of putting x, we plug in L. Tangent 0, x. Tangent is 0. Let's see. Inverse tangent is 0. Okay, it's just 0. This becomes 0. So that's our bounds. This bottom is 0, and this top is inverse tangent Lx. Okay. And now dx, see, because this dx here, this is going to turn into this. Okay, so let's go ahead and put this guy over here. Z secant squared theta d theta over the square root. Okay, I'll put the square root a bit later. So, you know, we have to substitute this here, this x squared. So it's going to be here. Instead of putting x squared, we're going to put this to the power of 2 right here. So go to the denominator. Now we have z tangent theta squared plus c squared square root to the power of 3. Okay. Okay. Yeah, so I'd say this type of stuff isn't really, like, probably exam worthy stuff was like where you just analyze the EX component. Like, I'm not sure if you see this in actual physics because these take a little bit, unless the solution is kind of provided to you already and you're just doing the limit analysis or the vector analysis. Okay, this is just math at this point. But yeah, okay, so now we look at this square root here. Square root z squared tangent squared theta. So I'm distributing this exponent to both the tangent and the z plus z squared. We have 2 z squares here, so we can factor them out. Now, this is equivalent to saying this. Which, again, something squared to like a square root. Man, my laptop's getting like hot. Okay. Oh, well, there goes the iPad. All right, let me troubleshoot this real quick. Let's see. Ah, there we go, we're back. Okay. Yeah, maybe I shouldn't do these videos too long. But okay, yeah, you get a z. Okay. Let's start the Apple Silicon. Anyway, this becomes, so yeah, this is a trig identity here. This becomes secant squared theta, okay? Tangent squared theta plus 1 is secant squared theta. Again, you have the squared and then the square root, so that cancels. So you end up with z secant theta. And then secant theta is 1 over cosine theta. This is also a trig identity, okay? And now we're going to plug this. What should I do? Oh, no. Let's not do this trig identity yet. Let's just leave it like this, okay? So Iy is going to be equal to, okay, 0 tangent negative 1 Lx z secant squared theta d theta. And now you have z secant theta to the power 3. Okay, because we dealt with this inside part. Now there's the third power here. Distribute this 3 into the z and the secant. These cancel, and you end up Iy 0 tangent 1 Lx. You end up with 1 over z squared. Secant squared over secant to the power 3. Now you have 1 over secant theta. D theta doesn't cancel. Okay, and now secant theta, now we employ this identity. Secant theta is equal to 1 over cosine theta. Okay. And Iy is now Lx 1 over z squared. This is constant. So you know what? We can actually bring that out. Here we go. We can bring that out. And now when you have something like this, through algebra, this just comes up. So it just becomes cosine theta, d theta, and the integral of cosine theta is sine theta. Okay. Iy 1 over z squared, 0. Actually, I don't have to do this anymore. So sine theta bounded from 0, tangent 1, Lx. Okay. Iy 1 over z squared sine of tangent Lx. So we're plugging in this tangent into here. Okay. That theta there. Minus sine of 0. Plugging the 0 into there. Fundamental theorem of calculus. Now sine of 0 is just 0. Okay. And we're left with this kind of expression here. Iy is equal to 1 over z squared sine inverse tangent Lx. Okay, we're still in the substitution world. We have to bring this back to reality. So recall, let's go here. So theta is equal to tangent Lx. Meaning that tangent theta is equal to L over x. And this, we can make an associated triangle here. Pythagorean triangle. See, I mean, it all comes back to the triangle, right? I mean, theta, and then this side is sort of the adjacent, the opposite side, and this here is the adjacent side. And so Pythagorean theorem, x squared plus L squared, the hypotenuse equal to the, so a function of kind of these components, Pythagorean theorem. And now, when you have something like this as a sine of tangent, so you kind of imagine this. You say a sine of this triangle here. That's essentially what this expression here means. And so the sine of this triangle is, again, opposite over hypotenuse. So opposite over hypotenuse. So this expression here becomes, okay, Iy 1 over z squared, okay, this whole thing here becomes L over the square root of x squared plus L squared. And now that we've solved kind of this integral here, we can plug it back into the electric field equation for the y component. This guy here, okay? So yeah, let's go ahead and copy paste, boom. So Ey is now equal to plus minus lambda z 4 pi epsilon naught 1 over z squared, okay? Because it, you know, we solved the integral, and that integral was this kind of y here. So now we just have to sub in all of Iy into here, okay? 1 over z squared, get rid of this thing, it's bothering me, okay? And, you know, times L square root z squared plus L squared. Okay? Now, now we're dealing with this equation here. So, okay, so the z's are going to cancel. Okay, so you're going to have ey plus minus lambda 4 pi epsilon naught z at the bottom, square root of z squared plus L squared. Okay. Oh, there's an L up here. Sorry. And I'm going to prepare this thing for limited analysis. Okay. Yeah, let's do that. So ey, let me see. Yeah, okay, so, yeah, let me prepare this for limit analysis. So we have to do a little algebra here, just to turn this into like an equivalent expression that favors more limit analysis. So I have L up here. Okay, I can factor out an L squared out of this expression. Okay, so I brought this out. I brought it out over here, meaning that if I multiply back in, I'll get back this expression. Again, square roots cancel with the L. So we end up having something like this. Square root c squared over L squared. Sorry, my notation is slurring a little bit. L squared plus 1. These L's cancel. No. This isn't ideal for limit analysis. In this case, what we want to do is this. What do we want to do? Yeah. So ey is equal to, yeah, we want to remember actually this formula here. We want to remember QL, the linear charge density formula. We want to plug it back in here. Okay. Q L 4 pi epsilon naught Z L square root of Z squared plus L squared. Now, this is the question that Griffiths was kind of answering in the beginning. What happens when Z goes to infinity? Okay, again, yeah, here, look at this. So the L's cancel, right? So let me sort of rewrite this. Okay, what happens when Z goes infinity, or is much greater than L, much greater than L? So again, in the beginning we said, like, okay, we expect to receive the the equation of a point charge, kind of in the same way with our EX component. Okay. So now if Z becomes really big, if you're like really, really far away from this rod, okay, meaning that it's so far off that the rod actually looks really, really small, okay, we expect this equation to go down to the equation of the electric field of point charge, okay, 1 over 4 pi epsilon naught Q over Z squared in this case, because Z is sort of the connection line, and you know, both these are positive, and you over here, okay, check this out. So let Z go to infinity. Let Z become infinitely big compared to L. What's going to happen here? Yeah, so in this limit analysis, you could see this expression as two ways. Okay, you could see it like, you know, 4 pi epsilon naught Z 1 over Z squared plus L. You could go ahead and say that this goes infinity, and then your electric field would just be 0, because you have these infinities in the bottom, that goes to 0, because you're dividing infinitely many times. Or you could see it this way. You could see that the length of the rod, comparatively speaking, you're so far away that the length is practically just nigh. Very small, 0. Okay? Infinitely small, something like 0. So L goes to 0, approaches 0, and our solution, okay, as it approaches 0. Okay, so perhaps, you know, so I'm very mathy. Let me kind of write it, you know, as L approaches 0, EY. Okay, I didn't do it for the other one, but for this one, you know, since it's a bit more serious, because this is kind of like the problem that Griffiths was talking about at the beginning. Let's see. So now, in this case, EY, the limit as L goes to 0, EY, and it becomes 4 pi epsilon naught Z 1 over Z squared plus 0 squared. Again, you get this cancellation of the square of the Z squared with the square root. So at this limit, you know, not 0, but going towards 0, the equation renders down to that of a electric field of point charge. See, because these two Z's, they multiply together, and you get Z squared. You know, or, you know, more, let me kind of drop this off, more familiar, 1 over 4 pi epsilon naught Q over Z squared, and there it is. So, you know, in some sense, this equation does hold, and I'd say for this one, we choose it to be positive. Because again, if her point charge is positive, this, you want the E field component to be in the y direction, the positive y direction, so up. And so yeah, so you know what? I'm going to leave it to you. What happens, I don't know, when the limit as z goes to 0 for this one, or the limit as L goes to infinity. Like, is it the same thing? Or I'll leave that to you. But I think if you watch this entire video, you might have a gist of how to employ this kind of limit analysis. Okay, it's like once you have these equations that are analytic, after you solved all the calculus, and you have these kind of solutions, you do the limit analysis. I suppose that you could do the limit analysis also when, like, with the integral forms of these equations, and you wouldn't have to do all this math. And you know what? I'll leave that to you. I did the heavy lifting. You investigate whether you can do the limit analysis in these kind of forms so that you don't have to solve these equations. Because sometimes these things are, for this case, it is solvable. Sometimes these things are unsolvable, and you just kind of leave them in this form and you use a computer to solve it. Yeah, I think that's probably an interesting idea, conducting limit analysis in non-analytic sort of solutions. Or non, fully solved solutions, where all you have is kind of your integral forms. Yeah, I'll leave that as an exercise to you. For now, let me kind of just end it. Let me go ahead and write the component equation here. So E, where, you know what? I want to bring out the other form of writing vectors, which is this form here, where you have this sort of vertical parentheses. At the top, I put the x component. At the bottom, you put the y component. Let me go all the way up to the x component. Wherever it is. Man, that was a lot of math. Here it is. Copy. Okay, paste it here. Oh my god, I copied nothing, I guess. I copied the equation and then I hit a button. I hit the white part and then I just copied nothing. Copy. Paste. 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 Alright guys, half of this is watching me struggle. Why is it not? Copy. Paste. Oh yeah, that's very interesting. Am I gonna have to write this equation cut, paste? Oh well, that's not good. Okay. All right, you know what? I'm just gonna have to memorize it and just write it, I guess. The copy function is. Maybe I'm doing something. My brain's kind of burnt a little bit. I mean, I think, explainably so. Okay, so let's just write the equation down. It's most certainly negative lambda 4 pi epsilon naught 1 over z minus 1 over the square root of c squared plus L squared. Something like this. And then the y component is this just positive lambda 4 pi epsilon naught. Z at the bottom. Yep, okay. No. Yeah, here it is. With the positive there, Z at the bottom, L. Yep. Okay. Z, L, square root, Z squared plus L squared. There you go. Ooh, that was tiring. Yeah, no, I mean, you know, imagine having a lecture in like an actual class that's only 50 minutes and trying to explain one of these problems. Like, it's impossible, I mean, you know. Yeah. Luckily, if I do a lecture, I'll have these videos to kind of help supplement them. Yeah. Anyhow, yeah, that's it. Let me kind of go back over here. Yeah, you know, if you stayed this far, thanks. Awesome. You know, I hope you got some from it. Oh yeah, there's still much problems to go. You know what? We're gonna do them some way, somehow. And yeah, please stay tuned, like and subscribe, do all those things you do in the YouTubes, and yeah, see you in the next one.